Hello everyone, my name is Cherradi, and today I'm going to present some joint work with my PhD advisor, Paul-André Méliès, titled Every Model Category Induces a Derivator Valued in Double Categories. So first, to set the background, given a category M with small limits, and given a functor U between small category, then we get a functor U star between the diagram categories associated to M, which admits a right adjoint functor denoted for real U or U with a subscript star, which is defined by a right-can extension along the functor U. Now we can add homotopy to this setting. Just consider a model category M with a class of equivalence W. Then every functor between small category induce this time a precomposition functor between the homotopy categories, where we take the localization with respect to the pointwise weak equivalences between diagram. It now has right adjoint defined by homotopy right-can extension. This leads us to the notion of derivators. Derivators were introduced by Grothendieck to axiomatize the situation, starting from a two-functor, strict two-functor, from cat up, where 1, 2 means that both the morphism and the two cells direction are reversed, into K, which is a given two-category with finite products. Historically, K is cat, the category of large categories. And note the action of this functor D on morphism U star. Such a strict two-functor D is called a prederivator. To get a left derivator from this, we need our prederivator to satisfy 4 axioms. The first axiom has to do with finite product. It says, first of all, that D of the coproduct is equivalent via the canonical map to the product of the D's. And moreover, the canonical map to the terminal object of K from D of the empty category is an equivalence. The second axiom has to do with detecting invertible two cells pointwise. Namely, given a small category A and an object X of K, and if we have a two cells phi such as in the following situation, so a two cells from F to G, it is invertible if and only if every whiskered two cell, such as this one, is invertible for every object A of the category A. The third axiom is just the statement that the functors U star admits a right adjoint for all U. And finally, the fourth axiom has to do with pointwise, the computation of pointwise can extension, in fact. So it says that the natural transformation alpha that is induced by the slice category A on B, where U is a functor from A to B, so we have a canonical comma square such as this one. Then if we take its image by D, then we have a two-cell alpha star, which we require the mate of to be inversible. So the mate of alpha star is just this one. We will require it to be inversible in the two-category K. This leads us to the important example of Quillen derivator. The starting point of our work is in fact the following key results due to Sizinski in 2003. The prederivator dm, which was defined on the slide about the homotopy coherent diagram, which is associated to a model category M. This prederivator is a derivator. This is the theorem. So we deduce from this a simplicial object in CAD by just precomposing with the inclusion of the category of simplices delta with n-dimensional simplex noted n between brackets into CAD. So this is a two subcategory of CAD. And we get this construction, which is inspired by Hammer construction that is due to Dwyer and Ken. Let us recall quickly the Segal condition. Given a simplicial object S in cat, for example, we have a canonical cone of this form, and we say that the simplicial object verifies the Segal condition if every such cone is a limiting cone in cat for every n larger than 1. Now we are able to state the main theorem of the paper. Suppose given a model category M and its simplicial object nerve M defined just as explained, and then we have established that the simplicial object nerve M satisfies the Segal condition. The two ingredients of the proof, two main ingredients in the proof, in fact, are the following. First, we rely on the three-arrow calculus in a model category that reduces homotopy to the existence of 3x3 diagram of the shape below. This is discussed in great details in a book by Dreyer, Hirschhorn, Kahn, and Smith, 2004. And the second ingredient is a notion called Quillen bifibrations, which is introduced by Kahn and Méliès in 2020, and which enables us to connect by pull and push the various zigzags in the previous diagram in M, which represent the same morphism in the homotopy category. Now we may rephrase what we've just said like this. Suppose given a category K with finite limits, a simplicial object in K satisfies the Segal condition, saying that it satisfies the Segal condition is exactly the same thing as saying that it is an internal category. It defines an internal category in K. When K is the category of large category, we may call such an internal category a double category. We have thus obtained a double category in a canonical way that we will call double M from the model category M, which has horizontal arrow dimorphism in M. So before localization, the vertical arrows the morphism in the homotopy category, therefore after localizing, and the double phase are related to the hammock construction. Precisely, the double phase look like this. So the conceptual definition of those double cells is in fact morphism of D of 1, and we may see it as represented by those kind of diagrams. So this is a double cell associated from F to F prime with vertical components U and V. And of course, we take the right-hand side to be a diagram in M that we consider only up to an equivalence relation that is akin to the hammock construction. We may now want to state, or rather to make the following observation. Given the simplicial object nerve M, in fact, it leads to a simplicial object in there, where there is the two category of derivator with pseudo-natural transformations and modifications. This follows from the nice result that shifting a derivator by a D by a small category, namely taking the following two functors dA, which associates to every small category B, D of A times B. This defines a two-functor which satisfies the axioms of a derivator. We are now in the position to state the second main theorem of the paper. By applying this shift construction globally, so defining a two-functor E that associates to every small category A the derivator dA, we have constructed a two-functor that defines a derivator in the category there, so a derivator of derivator. The key ingredient of the proof this time is a calculus of exact square in cat. We have established in particular that if we have two functors U and V in cat, then the following pullback square has induced is exact in the sense that the induced maze transformation is invertible. Finally, we might wrap up everything by saying that we have established that for every model category M, the previous derivator of derivator restricts to a derivator of double categories from the two category D up into double cat, where ready is the full two subcategory of ready categories in cat, and double cat is the two category of double categories. so seen as simplicial objects satisfying the Segal condition, pseudo double functors, and modifications. And this gives the name for this presentation. Thank you for your attention, and I may leave you with the reference. Thank you again.